Hello everyone, and welcome back to my course that is being offered online. And today we are going to focus on this topic of probability and statistics for data science. We are going to see how the basic probability and basic statistics can help a data scientist, and in fact it can go a long way in bringing out some inferences for the big data analytics as well. So yes, the word probability, probable, as the word suggests, often we make some decisions based on the probability. For example, if you're going out, based on the weather condition, you're making some decisions. For example, well, if the weather is too cold, then you want to wear a warm cloth. If the weather is too hot, you want to wear a thin cloth or short clothes. And moreover, based on the weather report or conditions or the data that you have in hand, you are in fact processing this data by yourself and making an insight, and accordingly you are taking an action. It's like you have this data, the weather data in your hand, and then you process it by yourself, and then you come to the conclusion that okay, today it's not going to be sunny, or today it's not going to be rainy. You know that. Or if you know, like for example, if you know that it's going to be rainy today, then based on that insight that you have come up with, you are taking an action, like you take the umbrella or raincoat or whatever necessary things that you want in a rainy day. Yeah, that's a very similar process that we have seen earlier, but this is in a very small scale. Let's see how this can be done, and in the long run how this can also help in some simple machine learning process as well as for our analysis, data analysis. So basically, like as an introduction part, I want to talk about this maximum likelihood estimation. Yes, in statistics, the maximum likelihood is a method of estimating the parameters of statistical model given observations. So here, this maximum likelihood estimation, it attempts to find parameter values that maximize the likelihood function. For example, like we are talking about weather condition, or we are talking about what would be the sales of a certain product in a shop, the maximum likelihood. Or if you're looking at the number of customers that are going to a particular shop, again, how much customers that you're expecting to be there. And for example, this week you have 100 customers, then the next week are you going to have the same number of customers? What is the maximum likelihood? Yes, it's kind of a simple observation by which you can estimate the likelihood of happening things that would happen, and that falls on the statistics. Based on the statistics, we can make some simple predictions. Well, in often case, as a data scientist, you want to make predictions, and we can also rely on the data that you have in hand, the statistical information that you have in hand, and often you can come up with some empirical results. And today we have many tools to estimate it as well. So I'll give you some basic overview of this probability and statistics, and it's going to be a long series of lectures where we will see actual impact of this probability and statistics for making data analysis. And in today's lecture, we are just going to focus on mainly on Markov chain process, and I'll just give you a brief introduction to the conditional probability as well. Okay, so this is an example of Markov chain estimation where, for example, suppose you are interested in heights of adult female penguin, but you are unable to measure the heights of every penguin population because it's quite impossible to reach out the place and measure the height by yourself. So assuming that the heights are normally distributed, with some unknown mean and variance, what you can do is that you can take a sample of the overall population. Say for example, if you have 100,000 penguins, then you are taking a sample of say 1,000 penguins and you are trying to estimate the value. So the value here that you are interested in is the height of adult female penguin. The same thing can be applied to other applications. You can think of various real world applications where we are looking at the probable values, the maximum likelihood values. Okay, as I mentioned, this is one of the thing that I want to discuss today. That's the conditional probability. So conditional probability is nothing but it's like a probability of an event given some other event has occurred. You know that one event has occurred, based on that event you are expecting another event to occur. So you can simply say this as like event A given event B. You are given with an event and then you are expecting another event to occur. So for example, you have this diagram and where you can see the weather as a whole, and inside this weather domain you have this rain, thunder, sunny, and some of the questions like what is the probability of a rain given we see thunder? What is the probability of a rain given it is sunny? The answer to this two questions seems to be very obvious. As you can see, probability of the rain given we see thunder, it's like almost 1. Like whenever there is a thunder, it seems that it's raining. And probability of a rain given it's sunny, again it's not that likely, but you can see there is a very lean chance for the weather to be sunny when it's raining. So as we move on, before I move on to this part on explaining some more examples of conditional probability, we'll stick to this example first. For example, here again there are a few more questions being raised. So you can see whenever there is a rain, you don't expect thunder every time, but whenever there is a thunder, there is always rain. So you can visually see under what condition what happens. So that is the basic idea of conditional probability. Anyway, the main goal here is to come up with the right questions. As in data science, our main objective is to come up with the right question. So that's the key part. So once you come up with the right questions, you know what you are expecting, and based on that you can decide what you can do. So now just take a moment and think by yourself, like in your research area or in your field of study, how can you use conditional probability? Given a condition or an event, you are expecting an event. So that's the basic idea we have seen, right? Probability of an event A given event B, that's the conditional probability. Yes, in real world there are lots of applications to this conditional probability. You can think about it. There are a lot of other things that we are going to cover, especially with regards to probability and statistics in data science. And today just I want to give you a brief overview of this conditional probability, and let's move on further to this Markov chain process. Okay, we will examine what is this Markov chain, and again, as the word suggests, it seems like a Markov is like a name, and chain is like a chain of events that could happen, right? Markov is a mathematician, Andrei Markov. He is the one who is the founder, we could say, founder of this Markov chain process and Markov process. And Markov process is quite simple. Like as you can see in this diagram, there are two states, state A and state B. In fact, state A and state E, and it's like, you can imagine, like it's like America and England, and whoever that is in America, the probability that he will be in America is 0.6, and probability that he will move to England is 0.4, and whoever is in England, he will be in England, the probability of being in England is 0.3, probability that he will move to America is 0.7. It's a simple observation, but in real time there are a lot of applications have been developed. Today almost in every field this Markov chain has been used, whether it is in engineering or biomedical or economics, all different areas they are still get benefited by means of this Markov chain. So what is the benefit? How we can benefit using this process? Let's examine this whole system and see how we can apply this. Okay, here is the simple definition of this Markov process and stochastic process. Okay, stochastic process is the movement through a series of well-defined state in a way that involves some elements of randomness. So you have a well-defined state, as we have seen earlier. We have state A and state E, so they are well-defined state. And these states, you are going to move from one state to another, the series of movement. So as in case of mathematics, this stochastic process and this Markov process, especially with regards to Markov process, we don't have this memory. So selection of next state depends only on the current state, not on the prior state. So this process is kind of defined and can be realized using something called transition probability. As we have seen here, from moving from A to E or E to A, or transition, it's kind of transition happening from one state to another state, and you have a probability of occurrence, and through this, in fact, you can come up with a matrix. So this transition probability is used to build those matrix, and we call that matrix as transition matrix or stochastic matrix or probability matrix or substitution matrix. In simply we can call it as Markov matrix. Yes, you can come up with this square matrix that could describe this whole event of the Markov chain. In other words, you have a real problem and you have modeled the real problem into this Markov chain of events, and then this Markov chain again been modeled as a matrix. So now our problem has been to deal with the matrix. Let's see how we can do that. Generally speaking, this is the exact overview or definition that we have seen with regards to Markov process. So Markov process is a stochastic process that has the Markov property. If the conditional probability distribution of future states of the process, conditional on both past and present states, depends only upon the present state, not on the sequence of event that preceded it. So this process is called this Markov process. So we can fully understand that they don't have memory, they don't care about the past historic information. All it needs is the present state, and based on the present state we can predict the future states. That's the simple process. So that's why before going into this Markov chain, I just want to highlight what a conditional probability is. Let's define more information about this whole stuff. And before we move on, I want to just give you this simple example. Let's assume that an urn contains 2 red balls and 1 green ball. So one ball has been drawn yesterday and one ball has been drawn today, and the final ball will be drawn tomorrow. and all of this has been done without replacement. Just imagine you have an urn, or you have a bowl, or you have a bag, and in this bag there are 3 balls in the bag, 2 red balls and 1 green ball. Yesterday you have picked up 1 ball, today you are going to pick up 1 ball, and tomorrow you are going to pick up 1 ball. So let us say that the ball that you picked up today is red ball. You know what it is, but you don't know what was picked up yesterday. We don't have the memory. We don't know the past event. But today's event, you are very sure that today is the red ball. Today is the red ball is what you got. Now if you want to estimate what is the future, that is what will happen tomorrow when you take from this bag, the probability would be 1 by 2, right? The probability that the ball would be red is 1 by 2. So that's because there are only 2 remaining balls that you can come up with, because you already picked up 1 red and you know that there is either red or green would be inside. So that's the basic thought, and with this basic thought you can actually see how this whole Markov process can be developed. And before we move on to this Markov chain process, I just want to highlight there are 2 more informations about this whole stuff. So the Markov chain can be processed in discrete time or in continuous time. As the word discrete time indicates, it can undergo transition from one state to another state on state space with probability distributions of the next state depending on the current state, not on the sequence of event that preceded it. Whereas for a continuous process, it takes in some state space and time spent in each state is non-negative real value. In other words, it can be any real value. So that's why we call it as a continuous one, not necessarily an integer value. And it has an exponential distribution. So in discrete time it has the probability distribution, whereas an exponential distribution is the kind of continuous distribution. And moreover, the behavior again, as with a discrete time Markov chain and continuous time Markov chain, the behavior of the system depends on only current state of the model, not on the previous states. Okay, so that we have already defined what is the Markov state. Let us define what is a state. The experiments of Markov process are performed at regular time interval and have the same set of outcome. So these outcome is called states, as we have already seen, and the outcome of the current experiment is referred as the current state of the process, and you can in fact represent that as a column matrix. So this is where we are trying to model the whole stuff. We are trying to model the states, the outcome of the states into the column matrix. Okay, so this is the transition matrix. So this transition matrix records all data about transition from one state to another state. We have this sample diagram picture that represents the whole transition matrix. You have the next state here and the current state. With respect to next state and current state, you can in fact build the whole transition matrix. There are a few points about this stochastic matrix. Stochastic matrix, the transition matrix, is any square matrix that satisfies 2 of the following property. One is all entries are greater than or equal to 0, which means that it cannot have a negative number. The other one is the sum of the entries in each column is 1. Remember, we are putting the next state information in this column matrix, and it is in fact the probability. So the sum of all the probability of that particular state should be 1. All transition matrix or stochastic matrix. So, that is the simple thing that you can keep in mind. Okay, now here it is. We are with this example. Let us say we are dealing with the stock, and here at the end of the day you have the price of a stock is given to you. So, based on the stock price by end of the day, can you predict what would be the stock price for the next day? Or in other words, can you see what is the sequence of events that would happen? So, let us examine it further. Say if the stock increases one day, the probability that the next day it increases is 0.3, remains unchanged is 0.2, and decreases 0.5. If the stock is unchanged one day, the probability that the next day it increases is 0.6, remains unchanged is 0.1, and decreases is 0.3. At the same time, if the stock decreases one day, the probability that it would increase the next day is 0.3, it remains unchanged is 0.4, it decreases is 0.3. Based on the given data, let us try to build up this transition matrix. So, can you quickly recall what was given to us? Just let us see pictorially, let us see what is given first to us. We are given with 3 states: increase, decrease, and unchanged. For example, the first one, what we have given with us, if today the stock price increases, the following day it might increase, but the probability that it might increase is 0.3, probability that it would remain unchanged is 0.2, probability that it would decrease is 0.5. In the same way, you can come up with the next 2 states. If today the stock price unchanged, what happens the next day? If today the stock price decreases, what happens the next day? It is just given in the problem. So, based on that you can actually come up with the whole transition matrix. Yeah, here it is. Increase, decrease, unchanged are given to us, and current state and next states can be seen. Okay, based on this observation, in fact, you can do lot of other process to examine what would happen in the coming days. So, that is a simple example of how to represent a transition matrix. Let us see into kind of using the real data. In fact, this is a problem and might not be the real one, but just looks like a real time scenario, because we are talking about a census studies that was taken in 1960s, and according to that it reveals that 80% of daughters of working women also work, and 30% of daughters of non-working women work. Assume that this trend remains unchanged from one generation to next generation. Remember, this assumption is very important. As far as the Markov chain is concerned, the assumption is quite important, and that might in fact affect the whole process later on. So, if 40% of women worked in 1960, determine the percentage of working women in each of the next 2 generations. So, here you are asked to determine the percentage of working women in each of next 2 generations. So, you have the data of 1960s and you have to determine the effect of this information and try to predict what happens the next generation and next generation. Let us see, let us try to plot this transition matrix with the given information. First of all, what is given to us is that there are two states: work, don't work. These are the two states that you have in hand. So, we are going to have the first column of the transition matrix, we are going to correspondingly having this state for work, and probability that a daughter from this state works is 0.8 and does not work is 0.2. So, that is given in the problem. Similarly, the daughters from the don't work state works with a probability of 0.3 and does not work with a probability of 0.7. Again, that is given in the problem. We have obtained these values based on the data given to us. Accordingly, you can come up with this transition matrix with regards to work and don't work. Fine. Let us see further on how we can predict what would happen the next state. So, for this we have to find the initial distributions or initial conditions. We know that from this problem we can see that 0.4 and 0.6 are the initial conditions. As if you like, I can just go back a little bit and show what was given to us. So, it is given that like if 40% of women worked in 1960, determine the percentage of working women in each of the next generation. So, we know that 40% of the women worked in 1960, which means that 60% they did not work. So, among the whole population we know that 40% of women worked, so that is 0.4, and 0.6, 60% they did not work. So, that is your initial condition. So, we are just referring it as 0 by the base of that column matrix. So, what we are going to do here is that simply take this value given to us, the transition matrix and the initial distribution, and we multiply this two matrix. Upon multiplication, you come up with this value, that is 0.5 and 0.5 as a column matrix. That gives you the information for the first generation. So, according to this problem, we come up with this 50% women work and 50% women do not work. This is one of the observations that we have. And remember that from 1960s to this one generation, the probability matrix or the transition matrix did not change. Again, you can find for the second generation. So, if you try to find for the second generation, you can see again there is this change happens. So, what we do is, in fact, we take the square of the given transition matrix and then multiply with that of the initial distribution. So, this can give us the actual results of the second generation, which is 55% women worked and 45 do not work. So, that is the observation that you get after two generations. Again, the assumption, you can take a note of the assumptions that transition matrix, the probability matrix did not change. Okay, in real time case, if you try to find first generation, second generation, third generation and so on, can you really get the actual distributions, or how long can you go as you go from one generation to another generation? So, as far as this Markov chain is concerned, because for one generation and another generation, you can see this has been locked, right, or it has been chained. The transition matrix has been changed from one generation to another generation and so on. So, likewise, you can consider this whole process is kind of blocked with the chains. So, that is why we call it as kind of Markov chain. Even you can consider if you this is one way of doing it. We are just squaring and using the initial probability and trying to find the second generation. And of course, you know what you should do for third generation, right? If you are looking at the third generation, you would probably go for cubes of it, and then you would take up this initial distribution. That's the way to do it. And there is other way as well. You can see here, suppose you assume that here is the probability matrix and this is your initial distribution, and you are getting the first generation information. So again, if you want to get x2, say for example, we can do the probability matrix with the first generation. If you want to do the x3 for the third generation, you can use the second generation. x4, again, the whole process can be repeated again and again. In the same way, on the other hand, we know that this is like p square or p power 3. You can look it in other ways. You can also go for p x naught, p square x naught, it's x naught with initial distribution, p power 3 x naught, p power 4 x naught. So this gives you x3, x4 and so on. So that gives you the whole information. Anyway, as I told you, you can keep on going or you can try to find further, but at one stage your value will reach a convergence point. So that is where you know that there is no more changes occur and your matrix becomes stable. Your the so-called the generation matrix that becomes stable. After that, you don't expect any more changes after that. After a point of time, this becomes stable. So we can do a lot of observation of the whole scenario. We talked about Markov chain process, and this process, can you see how it helps you to predict the future? We are talking about generation, but even it can be something like, you know, the data of information of a new product that you try to introduce into the market, and you know that what is its sales for this month, and based on that you can see what would be the sales for this product the coming month, the next month, and so on, and after how many months it would have a stable market. Yes, that can be observed. And there are a few more points of cautions that are needed as we talk about some real cases, whether it's generations or whether it's the product in the market. For example, the product in the market, it all depends upon the many factors, what kind of advertisements you are giving, what kind of efforts you make it to promote this product, and how about those competitors to that particular product. They don't remain quiet, they also take efforts to improve their market values. Yes, it all depends on various factors. So there is a tendency that we may have to come up with a better model than that of this the actual basic Markov chain. Or in other case, like we talked about first generation, second generation of women who work and who don't work, it can yield us a wrong direction, because sometimes we are talking about 1960s, and if it's 2000, 2050, all these periods are dramatically changing. The whole educational system, the whole society, the whole culture has been changing, and we know that what's happening behind the whole stuff and how it affects the output of the problem that we are seeing right now, like generations starting from 1960 onwards. Yes, what are the parameters? How does it affect the whole output of your system? But basically, these Markov chains are quite good in predicting as close as the true value, the so-called true value. But we have to be a bit of cautious about this. Okay, I like to stop here for a while, and then when we come back next time, I will do more information. I will give you more information on how this probability and statistics can be useful for data science. So we are still talking about data science, and we are still talking about how we can apply these methods for particular data analysis. We just talked about Markov chain today, in which we see how a prediction can be done, and basically prediction is quite useful for data analysis as well. So that's all we have for today. Have a nice day, and looking forward to see you in the next class. Bye.